Problem sheet 3, question 5. For an MM infinity Q with arrival rate lambda and service rate mu, derive the fact that the expected number of customers in the system, L, is equal to lambda over mu without using Little's laws. So let's think about what we know about an MM infinity Q. We know that the traffic intensity doesn't really make sense, but we do have a parameter theta is equal to lambda over mu that is going to be useful to us in a lot of manipulation. We also know the steady state probabilities of all the states. Those do not use Little's laws, so we can make use of those. We know that the probability of there being k customers in the queue or in the system is equal to theta to the k over k factorial times p naught, the probability there are 0 customers in the queue, and we know that p naught is equal to e to the minus theta. A further thing that's going to be useful for us to remember, and you'll remember these from your previous modules, is the series expansion of the exponential function. So we do have that e to the alpha is equal to the infinite sum from n is equal to 0 to infinity of alpha to the n over n factorial. Now with these tools in hand, we can start thinking about what is L. So L is the expected number of customers in the system. So that is the expected state. And we can write that as the sum over all the states of k multiplied by the probability of being in state k. Let's think about what is the first term of this. The first term is going to be 0 times by the probability of 0 customers being in the queue. That is just 0. So we don't really need to add that 0 term. So we could rewrite this as the sum from k is equal to 1 to infinity of k times pk, because that first term is just 0. So why don't we make this substitution? We know that that is going to be equal to k is equal to 1 to infinity of k times by theta to the k over k factorial p naught. And we know that p naught is e to the minus theta. So that's going to be the sum from k is equal to 1 to the infinity of k theta to the k over k factorial e to the minus theta. Now there's two things we can do here. We can factor out e to the minus theta from the sum, because the sum is over the k's and there's no k term in e to the minus theta. So we can think of that as just a scalar multiple. So we can factor that out. We can say e to the minus theta comes outside of the sum. And in this sum now we have k theta to the k over k factorial. But what is k over k factorial? That is just k minus 1 factorial. So we can write this as theta to the k over k minus 1 factorial. Now a clue here, we have this k minus 1 factorial and our infinite sum starting from k is equal to 1. That means we could rewrite this as a sum from some other index n is equal to 0 to infinity, n factorial. But we've got a problem with this theta to the k. So can we turn that into theta to the k minus 1? Well, yes, we can factor out a theta. So we can say this is equal to theta e to the minus theta. The sum from k is equal to 1 to infinity of theta to the k minus 1 over k minus 1 factorial. And now everything inside the sum is in terms of k minus 1. So we could make the substitution that if n is equal to k minus 1, we should be able to write this as the sum from n is equal to 0 to the infinity theta to the n over n factorial. And why is that useful? Well, this entity here, this is something that we can recognize as the series expansion of the exponential function. So we could write this as theta to the e minus theta times e to the theta. So that is just equal to theta. And remember, what is theta? That is lambda over mu, which answers the question.